Good morning, Professor. My name is Manish Chaudhary, and this project is titled as Malware Classification using the EMBER Dataset with Cloud Deployment. The goal of this project is to build a machine learning system that can classify executable files as either benign or malware, and demonstrated how such a model can be deployed and used in a real world setting. This project consists of three main tasks: training a machine learning model using the EMBER dataset, deploying the trained model using Amazon SageMaker, and creating an API-based interface system for real-time predictions. Together, these tasks demonstrate a complete pipeline from training to deployment and usage. The EMBER dataset is a large benchmark dataset used for malware classifications. Each sample contains 2,381 numerical features extracted from executable files. These features represent properties of the file such as headers, imports, and byte histograms. The dataset is balanced between benign and malware samples, which allows us to train a robust classification model. For the classification, I used multi-layer perceptron neural network. The architect architecture includes an input layer of 2,381 features, three hidden layers with 1024, 512, and 128 neurons, rally activation functions, dropout layer to prevent overfitting, and an output layer with zero classes, benign and malware. This model learns patterns in the feature space to distinguish malicious files. The model was trained using cross-interpret loss for classification, Adam optimizer batch size of 256, feature scaling using standard scaler, and hyperparameter tuning was also performed to improve performance. The model achieved strong performance on the test dataset with accuracy 90% approximately, precision 0.89, recall 0.90, and F1 score 0.90. The confusion matrix shows balanced performance across both classes, indicating that the model generalizes well and does not favor one class over the other. This is the confusion matrix graph here. For the cloud deployment, the model was packaged into a model.tar.gz file containing trained model weights, scalar, inference script, and the model pipeline involved uploading the model to Amazon S3, creating a SageMaker model, configuring an endpoint, deploying a real-time endpoint, and the endpoint successfully reached the in-service state. During the deployment, the AWS Academy environment imposed IAM restrictions such as S3 put object denied, S3 bucket denied. Because of this, full endpoint evocation was limited after debugging. However, the entire deployment pipeline was successfully implemented and the endpoint was created and initialized. To demonstrate a functionality, I implemented a local API simulation using a function called API predict. This function accepts a feature vector, applies preprocessing using the scalar, runs inference using the trained model, and returns a JSON style response. In this task, I deploy the trained malware classification model to Amazon SageMaker as a real-time inference endpoint. The deployment pipeline includes configuring AWS Access, uploading the model artifact to Amazon S3, creating a SageMaker model, creating an endpoint configuration, deploying a real-time endpoint, invoking the endpoint with a sample request, measuring API latency, and cleaning of AWS resources after testing. This task corresponds to task to deploy a model as cloud API from the uh, project requirements. The goal is to make trained model accessible through a cloud endpoint to external application can call it for inference. Here I have installed required libraries, which includes and these body 3 for interacting with AWS service, SageMaker for SageMaker utilities, tar file for checking model archived contents. Here I have imported the libraries. Um, uh, Here this section creates a border 3 session and initializes clients for Amazon S3, Amazon SageMaker, SageMaker runtime inference for security. AWS credentials should not be hard-coded directly in the notebook. Instead, they should be provided through the environment temporary AWS Academy credentials or a secure session configurations. Here in this section defines the SageMaker execution role, the S3 bucket name, the model artifact, and the deployment resources name. And these names are made unique with the current timestamp to avoid naming conflicts. And here I'll load the trained model and preprocessing components. Mm, And in the task 3, mm, the trained EMBER MLP model is used to perform inference on on-scene samples due to AWS SageMaker permission restriction, and the deployment endpoint could not be fully tested. Therefore, the inference pipeline is demonstrated locally, simulating the same input-output behavior as a cloud API endpoint. This includes loading the trained model, preprocessing input features using the saved scalar, generating predictions, returning a structured JSON like responses, and the model architecture used during training is redefined here to load the trained weights for inference. The trained EMBER MLP model was corresponding feature scalars are loaded for inference. The model is set to evaluation mode to ensure consistent behavior during prediction. Simulated API endpoint implementation uh, to mimic the behavior of deployment deployed cloud endpoint. The function validates input format, applies processing using the trained scalar, performs inference using the trained model, returns structured JSON like outputs, and mm, we here we uh, stimulates multiple API requests, uh, and this is the uh, mm, prediction for a new input, and mm, this measures how fast the system responds, mm, where the measured inference latency is extremely low, indicating that the model can process a request efficiently. This demonstrates feasibility of deploying the model in real-time malware detection system where fast response times are critical. Mm, and for the conclusion, the trained EMBER MLP model was successfully utilized to perform inference on unseen data due to the AWS SageMaker permission restriction encountered during the task 2. A simulated API endpoint was implemented locally to replicate the behavior of real-world cloud deployment. The system accepts future vectors as input, applies processing using the trained scalar, performs classification using the trained network model. The model structure JSON-like responses containing prediction and probability score. The simulated API demonstrated correct input-output handling and consistent prediction behavior. Additionally, the inference latency was observed to be very low, indicating that the model is suitable for real-time malware detection applications. Latency was measured using timing functions, and the response time is in milliseconds. This shows that the system is efficient and suitable for real-time malware detection. And this is the future work. And in conclusion, a machine learning model was successfully trained for malware detection. The deployment pipeline using SageMaker was implemented. API-based inference was demonstrated through simulations, and the system achieves strong performance and fast inference despite AWS restrictions. The project demonstrates a complete end-to-end machine learning workflow. Thank you so much.